Okay, guys, now let's start with chapter 2. Chapter 2, it's about counting techniques and probability. In this section, we're going to discuss counting sample points, and mainly our aim is to use some techniques to count the number of outcomes in a certain experiment. The first rule that we're going to discuss is product rule. We are saying here that if an operation can be performed in n steps, and these n steps, they are independent on each other, each of these steps, it has different ways, k1 different ways, step 2, k2 different ways, and so on, then the total number of different ways to perform is the product of them. We named it as product rule because we are multiplying these different ways. In order to understand it, here we illustrate it via a simple example. All of you know what we mean by die. Die is the one that it has 6 outcomes, 1, 2, 3, 4, 5, 6. And if we throw a die, either we're going to get 1, or we're going to get 2, or 3, or 4, or 5, or 6. But here we are asked how many sample points are there in the sample space when a pair of dice is thrown once. It means that we have 2 dice and we are throwing it at the same time. What are the options that we may get? We may get 1 from the first and 1 from the second, 1 from the first, 2 from the second, 1 from the first, or 6 from the second. So in die 1, how many options do we have? We have 6 possibilities. And in die 2, we have 6 possibilities. So the total number of outcomes is 6 from die 1 times 6 from die 2, which is 36 ways. Here we have another example. We are saying that if we have a 22-member club that needs to elect a chair and treasurer, how many different ways can these 2 be elected? Now, of course, here, guys, if we want to elect a chair and a treasurer, we cannot elect the same person as a chair and as a treasurer. So if we chose Bella to be a chair, we cannot choose it also to be a treasurer. Okay, guys? So just we can choose the same person only once. So here we have step 1 is the chair, step 2 is the treasurer. We want to choose the chair now. How many options for the chair? The chair has 22 options. From where we're going to bring the 22 options? We can choose any one from these 22 members. Now, we chose 1 for the chair. Can we choose this one again? Of course not. So how many options do we still have right now? We have 22 minus the 1 that we chose as a chair. So we have 22 for the chair, 21 for the treasurer. Then we're going to be having 22 times 21 using the product rule as different ways. Now we're going to talk about the sum rule. If you still remember, guys, in the product rule, we are saying and. Okay, so we need to choose a chair and a treasurer. So we have here multiplication. But in the sum rule, we are saying that an operation can be performed with step 1 or step 2, or it means that we have more than one option. Okay? When we say or, it means that we're going to use the sum rule, which is the addition of them. Here we have a direct example on it. We are saying that a password consists of 4, what do we have here, guys? Or 5 different letters. What do we mean by this one? If you want to set a password, either we can set the password as 4 letters, or we can set it as what? As 5 letters. So we are asking here, how many different passwords can be written? But again, guys, what do we have here? Different letters. It means that we cannot set the password, which is of 4 letters or 5 letters, as S. But we can choose it as SAMER, for example. Okay? So here, the first option, if we chose the password to be what? 4 letters. Of course, here we have to mention that we are using the English alphabetical letters. The number of English alphabetical letters is 26. So we have here 26. The letter that we chose it here, can we choose it again here? Of course not. So how many options should we have here? 25. Now, the options that we chose it here, can we choose it again? No, so we're gonna have 24. And finally here, we're gonna have what? 20. This is the case when we have the password of 4 different letters. What if we have it from 5 different letters? Again, we're gonna start 26, 25, 24, 23, 22. Then we have OR, so it will be the number of options of the first plus the number of options in the second. Okay, guys, let's move now to exercise number 4. We are saying how many even 4-digit numbers can be formed from the set as equal 0, 1, 2, 5, 6, 9 if each digit can be used only once, okay? So let's highlight whenever we have a question about counting techniques or probability, we have to do what? We have to highlight. So our set contains how many elements? 1, 2, 3, 4, 5, 6. It contains 6 elements. Each digit can be used only once, and it should be what? Even. What do you mean by even? Even is like 0, 2, 4, 6, 8. Okay? For a certain number to be even, it means that this part that is here, it should be even. But to have a number from 4 digits, of course, we cannot have here 0. It doesn't make sense to have it here as 0 because it will be of what? Of 3 digits. So what do we have till now? We know that our number is even. We know that this one, it should not be 0, and each digit can be used only once. It means that repetition is not allowed. So the cardinality of S is equal 6. Our first option is that when we have, either we have this one as 0 or not as 0. If it's 0, how many numbers do we still have here? From the 6, we chose here 0, we still have here 5. Can we choose the number again? Of course not. So we're going to be having here 4, here 3. How many options do we have? 5 times 4 times 3 times 1, which is 60. Now the second one, here we should not have 0. Here the case when it doesn't equal to 0, so we have only 2 options, either 2 or 6. Why? Because we are choosing an even number from which set? From the set as. Okay, guys, here we should not have a 0, right? And we should not have one of these ones. 6 minus the 0 minus 1 that comes from the 0, 5, minus 1 that comes from these 2 options, 4. Okay, guys? Now this one, it cannot be this number and it cannot be this number, but it can be what? 0. So we are removing this option and this option. We still have how many options? 4 options, and this one, 3 options. We're going to be having here 96 choices. We have OR. What do we do now? We add these choices together using the sum rule. Okay, guys, we talked about the product rule, we talked about the sum rule. Now we're going to talk about permutation. Permutation, from its name, it means that it's arrangement. Arrangement, it means that the order is very important. Let's give some examples when the order is very important. Guys, if you want to choose, if we have the first, the highest grade, or the first person in the class, the second level, the third level. Here we have levels. When we have levels, it means that the order is important. But we cannot do repetition. So in permutation, the order is important, but it's without repetition. We are saying here the number of permutations or arrangement of n objects in a row is n factorial. And of course, for those who forgot what do you mean by n factorial, n factorial means that we are multiplying n times n minus 1. We keep multiplying till we reach what, guys? Till we reach 2. So if we have 4 factorial, it will be equal to what? It will be equal 4 times 3 times 2. And by convention, guys, 0 factorial is equal to 1, and 1 factorial also is equal to 1. Okay, guys, also we are saying the number of permutation of n objects arranged in a circle is n minus 1 factorial. And the number of ways or arrangement to choose r items out of n items is p and r, which is n factorial over n minus r factorial, which is the same as the number of permutations of n distinct objects taking r at a time. Okay, guys, here we have an example. We have a president and a treasurer are to be chosen from a student club consisting of 50 people. How many different choices are possible if we have no restrictions? No restrictions, it means that out of these 50, we're going to choose 2. Arrangement is very important here because we have what? We have 2 different positions. So if Sam is a president and Maddie is a treasurer, it's not the same as saying Maddie is a treasurer and Sam is a president. So here we have 2 different posts. There are no restrictions. It means that only the order is important. Repetition is not allowed. So we have permutation, n is equal 50, r is equal to, because we are choosing 2, and we have p 52, which is 50 factorial over 48 factorial, 50 times 49, which is 2450. Guys, if any of you have problems in factorial, please let me know so I can explain it for you. Okay, guys, during the office hours or through email or through WhatsApp. Okay, in part B, we are saying that A will serve only if she or he is a president. It means that we have someone in the class or in the club that is insisting either if she wants to be chosen, she wants to be the president, or she doesn't want it at all. So here, how many cases do we have? We have 2 cases. Either we put A as a president or A is not a president. If A is a president, already the place for A is chosen. So we have only 1 case, which is A. Now, how many options for the treasurer do we have? A is chosen as a president. We still have 49 options. So here we have 49 options if A is a president. Now, if A is not a president, we have 49 options because A is not here. We subtract from the 50 minus 1. But also we cannot put A as a treasurer because she doesn't want or he doesn't want to be a treasurer. If he's a treasurer, he just wants to be either a president or not a president. So here we have 48 options. So how many options do we have? We have or, 2 cases. It means that or, we're going to add them up. In part C, we are saying that B and C are going to be serving together or not at all. What do we mean by this one? If we have Sam and Maddie, that they are always together, let's say. So they are insisting that either they're going to be treasurer and the president together, Sam, let's say president, Maddie treasurer, or vice versa, or they don't want to be, they want to be out of this election. So how many options do we have? The first option, if Sam and Maddie serve together, it means that the first one, either Sam or Maddie is a president, then we have here only 1 option for the treasurer. Okay, so here we have 2 options. Either Sam is a president and Maddie is a treasurer, or Maddie is a president and Sam is a treasurer. The other option, we are removing Sam and Maddie, which in our case here B and C. So we have how many options out of the 50? 48. And here, how many options should we have? 47. We have 2 cases. It means that or, so what do we have to do here? Add them up. Okay, guys. Now, here we have a restriction. D and E will not serve together. It means that if D is a president, E doesn't want to be a treasurer. And if E is a president, also D doesn't want to be a treasurer, and so on. Who's going to tell us now how many cases do we have? Either D and E are not president and not treasurer. So we have here how many options? Out of 48, we're going to choose 2. Or D is a president and E is not a treasurer. So we have 48 options. Or D is a treasurer and E is not a president. So we have also 48 options. Or E is a president and D is not treasurer. Or E is treasurer and D is not president. Also, we have 48 options. These are the only options that we have. We're going to add them up and get this one. But there is an easier method. We can check when can D and E serve together. D and E can serve together just in 2 ways only. Either D is president and E treasurer, or D is treasurer and E president. So for them not to be serving together, it's all the outcomes minus what? Minus when they are serving together, and we're going to get the same answer. Okay, guys, let's look at this rule or theorem. We are saying that the number of distinct permutations of n things of which n1 are of one kind, n2 of second kind, and so on is n factorial over n1 factorial, n2 factorial till nk factorial. I'm going to illustrate this one via this example, guys. If you are seeing here how many different letter arrangement can be made from the letters in the word Honolulu. If you look here, we are arranging the letters, but some letters, they exist more than once. Let's look at H. It exists only once. It exists 4 times. N, it exists 1 time. L, it exists 2 times. And U, it exists 2 times. The letters here, how many letters do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we put here what? 10 factorial. Over 1 factorial from H, 4 factorial from O, 2 factorial, 1 factorial from N, 2 factorial from L, and 2 factorial from U. Why didn't we put here the 1 factorial? Because 1 factorial is equal to 1. Here we have another example. We are saying in how many ways can 7 graduate students be assigned to 1 triple room and 2 double hotel rooms during a conference? So how many students do we have? 7 factorial. We need to put 3 in 1 room, 2 in 1 room, and 2 in 1 room. Okay, guys? So look at this one. N1 of 1 type, N2 of 1 type, and N3 of 1 type. It will be 7 factorial, 3 factorial, 2 factorial, 2 factorial, and of course, we need to find its answer. Now, the last thing that we're going to explain for today's lecture is the combination. But we're not going to solve on it today lectures. Hopefully the next lecture it will not be long. Just we're going to solve around 5 exercises to make sure that you understood the lecture of today. Here we use combination usually, which is denoted in this way: n factorial over r factorial and minus r factorial, when we do not have repetition and when the order is not important. What do you mean by when the order is not important? Suppose that, guys, we are in class and someone entered the class and said that I need 3 volunteers out of this class, from this class. So is the order important? The aim of this person that came to our class is just to take 3 out of you as volunteers. So here we do not have order. So we're going to use what? Combination. And also we do not have repetition. Why? Because if we need 3 volunteers, we cannot take the same person as a volunteer 3 times for the same event. Okay, guys? So we are saying that this is the number of ways to choose R items out of N items where repetition is not allowed and the order is not important. So again, guys, if you want to solve this exercise,